All right, let's get started with this online lecture in reinforced concrete on the behavior of shear in reinforced concrete beams. Just a few announcements for those of you watching this on Monday when we would be normally having this lecture. Just recall that homework 5 on T-beams and doubly reinforced beams is going to be due Wednesday, March 7th. Also, don't forget that the Army Corps of Engineers is having their recruitment day at Marshall on Tuesday, March 6th in the lobby of the Student Center. So let's get started looking at shear in reinforced concrete beams. Go ahead and get my lecture notes pulled up. Full screen mode. Okay. So what we're going to do in this lecture is go through some of the basic provisions for how you address shear in reinforced concrete beams. We're not going to get into design for shear in this lecture, but we're going to cover some of the basic fundamentals that you'll need in order to develop a procedure for design. So let's just start back. Let's just start at basics to try and get everybody into the mode of discussing shear and reinforced concrete. So let's keep it simple. Let's say we have a simply supported beam, uniformly distributed load. I think we've sort of beaten moment to death throughout the early part of the semester because that's really all we talk about. By now, for a scenario like this, everybody should know that the simply or the maximum moment due to a simply supported beam subjected to a uniformly distributed load is WL squared over 8. And that's just, your maximum moment at midspan. For any other scenario, you of course have, options. You can just break out pencil and paper and do some structural analysis. You can use one of the design aids. You could run it in RESA or something like that. So there's a plethora of different ways to do that, but that's looking at moment. Don't forget there's also shear going on as well. So recall that if you had a simply supported beam with a uniformly distributed load, the shear diagram would look something like this. You'd start off at the left end of the beam, you would go up so much for your reaction, and then you have a distributed load. So if you recall, distributed loads go down in sort of a sloped fashion down to the right support and then goes back up to 0. So just like with moment, we have to provide reinforcement inside a reinforced concrete beam for shear, and we do that through the use of stirrups. So if you look at a reinforced concrete beam, imagine you had some sort of X-ray view into the beam, you would see these sort of hoops going along the span. Those hoops are there primarily to resist shear forces in the beam. Now, one of the things you'll notice if you sort of pay attention to the diagram, you'll see that here at the supports, you'll see that the hoops are spaced really close together. But if you go into the main part of the span out here in the middle, the hoops are spaced very far apart. Well, that goes back to the shear diagram. You have very high shears here at the support, so you have a lot more stirrups. Whereas in the main body of the member where the shears are very low, you don't need as many of them. So that spacing patterns should make some pretty reasonable sense. Now, so let's ask a question. What happens if you have a concrete element and it's loaded in shear? So I'm gonna go back to a topic that you probably haven't looked at in a long time, and you don't need to be you don't need to remember all of the equations or any of the conversions or anything like that. It's pretty straightforward from a conceptual standpoint. I want to go back to Moore's circle. So if you recall, Moore's circle is a tool that we use as engineers to investigate stress states at different orientations. And this is probably a question that you had on a mechanics of deformable bodies final or something like that, or your homework assignment or something of the like. But the long and short of it is, if you have an element that's under pure shear, and you try and determine the principal stresses, what you find is two things. You find that your principal orientation is at an angle of about 45 degrees, and your principal stresses are equal and opposite. So the idea is if I'm shearing something, if I have an element and I'm shearing it, imagine that you have a ruler in your hand or a bar in your hand and you're shearing it. You're taking your left hand and moving it up and your right hand and you're pulling it down. and you hold that in place, what Moore's circle is basically telling you is that that element, that material, is going to want to fail at an angle of about 45 degrees uh, according to the stresses that you see here. Now, what happens in real life is just that, especially with reinforced concrete. So what I have here is an image of a lab test where a reinforced concrete beam has been loaded in shear, and you'll notice that the cracks really do follow that given pattern. So here in the image on the left, you can see this is where the support reaction would be. You can see this right here. This is sort of the support right there. And then here's where it's being loaded. So there's a massive force being pushed down right here, and that's the reaction pushing up. So that element is in shear. If you notice, all the cracks are at a 45-degree angle, so that makes sense from a Moore circle standpoint, but it also makes sense that the cracks are going this way. Because if you go back to Moore circle, the orientation specifically states that compression is going this way, but tension is going this way along the direction of the mouse pointer I'm moving. So if you notice, the concrete, it's sort of opening up this way. You can see where the crack's running this way, the concrete is wanting to separate along this axis. That's why it's separating this way, because in this direction, it's experiencing tension. And as we know, concrete's weak in tension, so it's wanting to crack that way. Now, the way that we arrest those cracks and we prevent them from happening is by including stirrup. So that's really the main purpose, is to try and account for that. Now, the way that we account for um, the nominal capacity of a concrete element in shear is pretty straightforward. Instead of looking at it from a sum of moments perspective, we look at it from a sum of forces perspective. And it's actually a lot simpler to determine the capacity of an element in shear. You'll find that determining phi Vn is actually a lot easier than determining something like phi Mn. So let's go back to our basic design expression. You know, up until now we've been using phi Mn is greater than or equal to mu. So basically saying that the moment capacity has got to be greater than or equal to the applied moment. Well, here we're saying that the shear capacity has to be greater than or equal to the applied shear. So let's talk about the shear capacity, because the applied shear, that's basically just this. That's just our structural analysis, and that's pretty straightforward to compute. What's new and what we need to take some time discussing is phi Vn. So a couple things. Uh, the way that we compute our nominal capacity in shear, the phi Vn component, is pretty simple. First off, Vn is just the shear strength provided by the concrete plus the shear strength provided by the steel. See, it's not a moment. We're not having to do force times distance and force times distance. We're just adding up our forces. So it's the shear strength provided by the concrete and the shear strength provided by the steel. Just add that up, and that's the total shear capacity of the section. That's the nominal strength of the section. You know, once we hit that load, the beam's going to want to fail in shear. So that's Vm. As for the phi value, one of the things that you'll find in shear is that because we're not looking at moments and because we're not looking at strains that vary along the depth, instead of having to go through a process to determine what phi is, because of the nature of the nature of the effect, phi value is pretty simple. For shear, always for shear, our phi value is taken as 0.75. So that's a pretty easy value to determine. Now, how do we determine each individual component? Well, we determine each individual component through a series of either empirical or mechanistic equations, and I'll explain that here in a moment. So first off, shear resistance provided by the concrete is pretty straightforward. It's an empirical expression. Again, that square root of FC prime is rearing its ugly head again. So remember, you put in PSI and you get out PSI. So to determine the shear strength provided by concrete, it's 2 times lambda times the beam width times the effective depth times the square root of FC prime. So because your beam dimensions are usually in inches and square root of FC prime is going to be in PSI, when you compute V sub C is going to be in pounds. So just be aware of that from a unit standpoint. V sub S is pretty straightforward as well. V sub S is basically computed as the area of your shear reinforcement, the area of steel, but we'll have to define that here in a little bit, times your yield stress of your shear reinforcement, times this quantity N. And this quantity N is basically just the number of bars per beam depth. So the way that we compute that is we just take our effective depth and divide it by the stirrup spacing. Now, reason why is because what we're looking at is, let's say that you have a reinforced concrete beam that's undergone, some failure. So you've had to overcome the shear strength of the concrete, and now you also have to overcome the yield stress of the steel in order to fail it. Now, if here's the crack, again, we're assuming an approximate 45-degree crack. This D over S quantity is basically saying, okay, imagine this is my D value, and here's my S value. The idea is, well, how many stirrups fall inside a given 45-degree crack? And a simple way of computing an approximate value is to just take D over S. So, for instance, if I had an effective depth of 24 inches, and S was 6 inches, you could assume that you'd have 4 stirrups within that given cracked region. That'd be a pretty simple and safe assumption to go off of. Now, the other thing that you have to be aware of is looking at when you compute AV. This image here on the left is a really nice example of that. So, looking at this from a force standpoint, the force inside each one of these stirrups is the area times Fy. But the area, you have to be very careful when you're computing the area. If you look at this three-dimensionally, if I look at the area of this one stirrup, okay, let's say this stirrup is a number 3 bar. So let's say this is a number 3 bar. So the area of a number 3 bar is, as you can see here on this chart, the area of a number 3 is 0.11 square inches. But for the area in shear, we would not use 0.11, we'd use double that. We'd use 0.22. And the reason why is, again, looking at this from a two-dimensional standpoint, you're going through an entire stirrup. Well, that entire stirrup here, we're cutting through 2 bars. So in this instance, AV would be 2 times the area of your stirrup, or the area of that bar. So if this was a number 3, it'd be 0.22. If it was a number 4, it'd be something like 0.4 or what have you. So this is just an image of some typical stirrup arrangements that you can have in reinforced concrete elements. So for instance, for these two, your area in shear would be 2 times your bar area. For instance, this one here in the middle, this would be 1 times your bar area, because there's only one stirrup leg going through that crack. So you can probably guess how much would be in this one. This would be 4, because you have 1, 2, 3, 4. So a simple way of doing that, just imagine you're cutting a section right through the middle of right through the middle of the beam, and asking yourselves, how many bars am I cutting through? So this would be 2, 2, 1, and then 4. So that should be pretty straightforward. Now, a couple of notes regarding reinforcement. This isn't going to be so important from an analysis perspective. We're going to use these values later on when we design a reinforced concrete beam for shear. They're basically going to provide us limits and means for selecting our stirrup layouts. But for now, I just want to throw them out here so that you see them. ACI has a couple limits on stirrups, just for safety and construction, ease of construction for safety requirements. So a couple notes. First off, ACI has a minimum reinforcement requirement that states that the minimum reinforcement is computed as this fraction, B times S divided by your yield stress, times the maximum of these two quantities. And that's very similar to what we had for tensile reinforcement in beams. We're not going to use this equation directly to look at AV. What we're going to do later is we're going to use this equation to help us sort of back calculate what S needs to be in order to achieve that. Because typically you're using a set stirrup size from a design standpoint, and really it's the S value that you need to determine. That's basically what you're determining in shear design is your stirrup layout. But we'll get to that later. There's also a maximum stirrup spacing that you can use or that you need to adhere to. So in regions that you need stirrups, um, even if you don't need that many of them, you still need to space them out a certain amount so that they're effective. So your S max is either the minimum of D over 2 of 24 inches or the minimum of D over 4 or 12 inches, depending upon what your VS is. It's not that big of a deal at this point. Again, these values will come in more from a design standpoint. We'll reference these later. What I want to do is do a very brief example just to sort of show you what's going on with the math and the equations. It won't get too hectic or too heavy. One of the things that you'll note is I've actually given you the answer in slide 190, so it's not that big of a deal if you need to go back and review. But let's sort of take a look at this. So I want to assess the shear capacity of the following beam. Now we're using 4 KSI normal weight concrete. We're using 60 KSI steel for the stirrups. As for the stirrups, we're using number 3 stirrups. Now, I've also given you the fact that the beam is 24 foot long. It's simply supported, and these are the dead loads and live loads. We'll go ahead and assume for the purposes of this example that these loads include the self weight of the beam. I've got here the dimensions. B is 12 inches, D is 24. I've provided H, but we're not really going to need that for this example. We're really only going to need B and D. I've also got a stirrup layout. So if you notice, stirrup or region 1 uses a stirrup spacing of 4 inches. Region 2 uses a spacing of 8 inches. Region 3, 10 inches. Region 4 of 20. We'll talk later on specifically about how you lay that out. You know, what's a good number of regions, because that's sort of an involved discussion. But right now, I just wanted to give you kind of an idea of what shear stirrup layouts would look like. Now you'll notice the shear stirrup layouts that you see start at a support condition and go all the way over to the center line of the beam. Imagine that this center line is a big mirror. You know, reflected on the other end of that center line is going to be that reinforcement pattern repeated. Most times in reinforced concrete design, especially when everything's symmetric, you only need to design shear reinforcement up until the center line, and then you can just repeat that in a mirrored fashion on the other end of the beam. So what I want to do is I want to go through some basic math and sort of demonstrate that this beam is equivalent, or that this beam has sufficient capacity. But in order to do that, we kind of need to do some basic math. So give me 1 second here. Okay. So what we're going to do first is we're going to look at this from a capacity standpoint. We're going to look at phi Vm. So the first thing I want to do first is I want to look at the concrete capacity. Or VC. Okay. So if you recall, we know that FC prime is 4 KSI or 4,000 PSI. Now we know it's normal weight concrete, so lambda is 1.0. This is actually the same lambda that we use for F sub R, so that makes our life a little easier in terms of remembering stuff. B was 12 inches, and H is 24 inches. So to determine VC, it is 2 lambda BWD square root of FC prime, which is 2 times 1 times 12 inches times 24 inches times the square root of 4,000 PSI. And remember, square root of FC prime, you always put in PSI and you always get out PSI. Now, if you chug that out, 2 times 1, that comes out to be 36,429.4. That it just literally taking the numbers and plugging and chugging them in a calculator. However, you got to be cognizant of your units. We're taking inches and inches and multiplying them times psi. So this is in pounds. So if you want to convert to kips, you have to divide by 1,000. So that comes out to be 36 point, we'll say, 43 kips. Okay. And while we're at it, let's go ahead and compute phi VC. Okay, so phi VC is just taking this value and multiplying it by phi. Remember, for shear, phi is always 0.75. So 36.43 kips. Okay, and I'm just going to track all the decimals times 0.75. That comes out to 27.32 kips. Okay. All right. Now, to sort of demonstrate something, I'm going to take I'm going to go off to the side, and I'm actually going to look at this from I'm going to look at this from an analysis standpoint. I want to look at the loads on this section. So let's see. Let's go back to this. Let's see. So here's our beam. And if you recall, we have a beam that's subjected to a dead load of 1.5 kips per foot and a live load of 3 kips per foot. Now, for the purposes of this example, we'll go ahead and assume that the live load is already reduced. So we won't have to worry about that. Now I'm going to conservatively, or it's actually, I'm going to say it's unconservative. I'm going to just go ahead and assume, just for simplicity in this calculation, that the dead load includes the beam self-weight. That might not be accurate. And if you're unsure, obviously go through and calculate that self-weight and add it just to be sure. But it's not really going to matter in terms of the comparison I'm going to make. So let's just take a second here and let's look at factored loads. Okay, so we have a dead load of 1.5 kips per foot, live load of 3 kips per foot. You know what? While we're at it, let's go ahead and add our self-weight. Let's just go ahead and do that. So our self-weight is computed as the unit weight of concrete times B times H. So let's go ahead and do that. Let's just go ahead and get some practice in. Um, this would be a good thing to practice. For those of you that if you had any have had any issues on some homework assignments with this is a good thing to go ahead and practice. So 0.1. Getting ahead of myself there. 0.15 kips per cubic foot times 12 inches, and then H was 27 inches times 1 foot squared over 144 inches squared. Let's go ahead and compute that. Let's go ahead and add that. So 0.15 times 12 times 27 divided by 144. That's 0.338 kips per foot. So therefore, we'll go ahead and assume that dead load is not incorporated. WU is 1.2 W naught plus W dead plus 1.6 WL. Okay, so that's 1.2 times 0.338 plus 1.5. Ooh, I forgot to put my units. Always put your units. plus 1.63 kips per foot. All right. Let's chug that out. All right. So that is 7.005 kips per foot. All right. Now, it might be tempting right now to go say, all right, mu is WL squared over 8, but we're not looking at moment, we're looking at shear. So a couple things, let's pull this up. So this should be fairly familiar. This is our simply supported beam uniformly distributed load analysis. Now, I really want to sort of take a look at the shear diagram here on the left. So one of the things you'll note, where is your maximum shear? It's always at the supports. Now to compute that maximum shear, we just use WL over 2. So I'm going to use WL over 2 to compute the maximum shear. But the big thing to point out is that the shear changes along the span. Specifically, it's a line. Well, if you look here on this second bullet, this tells you what the equation of that line is. And these things are going to be very important later when we look at shear design. Being able to determine not just what is the shear right here, but what is the shear along the beam is going to be very important. So that's just a point I wanted to make for later. So for right now, we're going to, for now, just for demonstration purposes, let's just look at the reactions, the maximum shear, WL over 2. Let's see. Oh, wrong one. Okay. So if we look at our reactions, so let's do that. So R is WL over 2, which is 7.005 kips per foot times the length was 24 feet divided by 2. So RU is 84.06 kips. This is actually a really important value to look at, especially when you compare it with this. So let's just make sure everybody's clear on what we're talking about here. The factored loads, the RU of 84.06 kips, that is the maximum force in shear. That is the maximum load in shear we are applying to the beam. The beam by itself, if we didn't put any stirrups in it at all, the capacity of the beam in shear would only be 27 kips. That's just the shear capacity of the concrete by itself. So the concrete by itself is certainly not strong enough to hold up those loads, hence why we need to include stirrups. So let's look at the capacity in shear of the stirrups. Now there's 4 different regions, so we're going to take each region one at a time. So steel capacity, and we'll say steel capacity region 1. So for region 1, we know that S is 4 inches. Okay, and I got that from right here. This is the shear stirrup layout. We're looking at region 1 right here, and S is 4 inches. So because of that, what we can do is this. We can start off by computing our nominal capacity in shear, which is just AV times FYT times D over S. Okay. Now, let's take each of these one at a time. AV. Okay. We have number 3 stirrups. Okay, these are number 3 stirrups. Number 3 stirrups, the area of a single number 3 is 0.11. So in our scenario, we have sort of what's called a U-shaped stirrup because it kind of looks like a big U. But remember, cut a section right through the middle of that beam and we're going through 2 bars. So for AV, instead of using 0.11, I'm going to use 0.22. All right. Fy, take that as 60 KSI. And as for D over S, that is 24 inches over S, which in this case is 4 inches. So plug and chug. That is 79.2 kips. All right. VVS is just taking that and multiplying it by 0.75. So that is 59.4 kips. And then now that we have VVS, we can go ahead and compute VVN, which is just VVC plus VVS. Okay, now VVC, that was 27.32 kips. And here is a perfect example of making sure that you're cognizant with your units. If you don't convert VC, you're liable to put VC in pounds and VS in kips. So just make sure you're consistent, make sure you're diligent. That is 27.32 kips plus 59.4 kips. And now we're getting 86.72 kips. Now this is starting to look a little more reasonable because we've got VVN is 86.72 kips. And remember, our reaction was 84. So now starting to look a lot more reasonable. Okay. Now, that's for region 1. The only difference between region 1 and the and other regions is just the change in S. For instance, if I go here, if I go and look at this, the only difference between region 1, region 2, region 3, and so forth is just the change in S. So region 1 S is 4 inches, region 2 S is 8 inches, region 3 S is 10 inches, and so forth. So what I'm going to do is, I would just repeat this over and over again. Instead, I'm just going to summarize this in a pretty nice, neat little table. So I'll say for remaining regions, getting ahead of myself again. For remaining regions, okay. So, okay. So we'll say range. We'll say S. We'll say VS. I should have warned you there's going to be a table that goes along with this, but I've only got one more column. Okay. All right. So I'm going to just sort of summarize my results in a neat little table here. So let's start off with region 1. Now, what I'm going to do here for region 1, I'm going to skip the range part for right now, but in region 1, S was 4 inches, VS ended up being 79.2 kips, and then VVN was 86.72. Okay, now I'm going to skip the range part for now, but let's look at region 2. Okay, region 2, the only difference is 8 inches. Okay, S is 8 inches. So this is 8 inches. So what you would do is everything that we did up here up top, all this info up here, literally just replace, instead of 4-inch spacing, use 8-inch spacing and just plug and chug. Now when you do that, what you're going to get is this is 39.6 kips and this is 57.02. Which should make sense if you think about it, because if we're talking about a situation where the stirrup spacing is getting larger, that means there's less stirrups. Less stirrups means less capacity. So the capacity should go down. And you can practice it. You can plug and chug it. It's literally just taking the number in and just redoing the calcs. For region 3, S is 10 inches, so the numbers are going to go down just a little bit more. This is, when you plug and chug, ends up being 31.64 kips. So this is, let me see, can't quite read that. Give me one sec. 58.96. Actually, give me 1 second here. Oh, no, I see what I did. Give me 1 second. There we go. That's right. So I'm getting 51.05 kips. Okay. So that's region 1, region 2, region 3. Now what's going on in region 4? Well, in region 4, there actually are no stirrups at all. Okay. Now region 4, so what I'm going to do in region 4 is the stirrup spacing. It doesn't really matter what the stirrup, whatever you put stirrup spacing. It doesn't. There are none. If there are no stirrups, then the capacity of the section, the steel capacity in shear is 0. So if there is no shear capacity, what is or if there is no shear capacity provided by the stirrups, then the ultimate capacity of the section in shear is just 27.32 kips. And that value right here, that's just phi-VC, because VS is 0. Remember that phi-VN is phi-VC plus phi-VS. Remember that. So if you don't have a VS, then it's just phi-VC. Okay. Now, the one thing I left out are these ranges. And the ranges are pretty simple if you think about it. I'm going to report the ranges in inches. So let's look at this. So what I mean by the ranges is sort of, if you were trying to plot this, if you were trying to plot these capacities as a function of span length, you'd have to have a common origin. So let's say for simplicity, let's say that this right here, our support condition here at the left side of the beam, let's say that that is x equals 0, if you will. So this is x equals 0, so you can almost think like x equals 1, x equals 2, so on and so forth, all the way over here to x equals 52. So what I'm going to do is this. I'm going to say that region 1 goes from 0 inches to 52 inches. Now, that's region 1. What about region 2? Well, region 2 is 32 inches long. So if this is from 0 to 52, this is from 52 to whatever that adds up to be, 52 and 32, that's 84. So 52 to this is 84. So this is 52 inches to 84 inches. So the next one would be 84 to whatever this is. And let's see. So 84 and then 40 inches, that makes 124. 124 to this makes 144. So hopefully that is pretty easy to follow. The reason why I wanted to include that is I kind of wanted to show you what's going on with the capacity, and really the whole point of the example. So what I want to try and do is I want to do a plot. So let's, oh, I can do better than that. All right. Let's say that this is X, and let's say that this is shear. Okay. So let's sort of take this one step at a time. So from x equals 0, so this is x equals 0, to about, we'll say right here, where x equals 52 inches, our capacity is, we'll say what, 86.72 kips. That's our capacity. Then, here's what's going on. Let's look at our beam. What's happening in region 1 is we have stirrups that are they're spaced very closely together. Once we get out of region 1 and we're in region 2, the spacing suddenly changes. The spacing suddenly goes from 4 inches to 8 inches. So because the spacing goes from 4 inches to 8 inches, the capacity suddenly drops. Specifically, it drops to 57.02. So going forward, that's 57.02, I should say. This is 57.02 kips. And that's going to keep going until x equals 84 inches. Actually, let me see if I can erase that a little bit. Sort of squinch that in a little bit. We'll say it's about right here. And here at x equals 84 inches, that's going to drop even further. So this part here is going to go away. So you're going to kind of get this sort of stair-step plot going, where the farther you get away from the support, the lower the capacity is going to be. That's going to be 51.05. Maybe if I try and draw it to scale, it really looks more like this. Maybe something like that. That's 51.05 kips. All right, and that goes up until about here, maybe about right there, where x equals 124 inches. And right there, the capacity drops even further. Let's see if I can erase that. To 27.32 kips. And that will go on until we hit probably about right there, where that is x equals 144 inches. But one of the things about that point right there is that is the center line for the whole beam. Okay. Now, so what we've got here is a plot. This is looking at the shear capacity of the beam as you go away from the support. What's really most important, though, is not just this by itself, but comparing that against the forces. If you go back to our slide handout and look at this, this really tells it all. So what we have here in this slide is exactly the results of this example. So this red dashed line that you see here, this is obviously a scale. I did this in Excel, but this is looking at the capacity of this beam along the span. So if you notice, I have the I have, 1, 2, 3, 4 regions. Each of those regions represents the 4 FEVN values I just computed. But the biggest thing to reveal is this. This is the shear diagram. That's the shear diagram of the beam. Now, how do you compute that? Or how do you plot that? It's right here. Vx. So here's our equation. Vx equals W times the quantity L over 2 minus X. Just plot that out. So you can do this in Excel. It's actually quite easy. I'm going to do this. We've got time, so I'm going to go ahead and show you how I generated this plot in Excel. So let's go through that right now. All right. So okay, X is in inches, VU in kips. Okay. Now, just so I don't have to keep going back and forth, let's snip that. Oh, goodness, that is big. Let's squinch that down a little bit. Here we go. So that's the equation that we're going to use. So this beam is 24 feet long. So L is 24 feet, or what is 24 times 12? 24 times 12. It's 288 inches. Okay, I got to make sure I'm consistent with my units, so let's make sure that everything is in inches. Okay, so let's plot this out. So 0, 1, 2, 3. And let's go all the way to 144. Let's just plot for half the beam. Ooh. Okay. Okay. So equals, so let's plot our shear. So what we'll need is W. If you recall, we already computed W here, and W was right there. This was our W value, 7.005. So 7.005 times, oh, got a 6 there, 7.005 times L over 2, so 288 over 2 minus X. Oh, there we go. This right here, this is perfect. This is perfect. So this is where units become so important. So actually, let's not be lazy about this. So watch this. Okay. So this is the span length in inches. Okay. Now that load I just computed or just wrote down was 7.005. But what were the units? See, this is perfect. That was kips per foot. Kips per foot, this is in inches. It's got to match. So how do I convert this into kips per inches? I take that and I divide by 12. So you got to make sure you're consistent. I'm going to take this, I'm going to divide it by 12 in my formula, and there we go. Now I know I got the right answer because the shear at the beginning of the beam is 84.06 kips, and that's the same thing I computed as the reaction earlier. So that gives me a check that what I'm doing is correct. Fill that in. Everything looks good. Let's highlight all this and insert a scatter plot. Bam. There is our shear diagram. There's our shear diagram. What I'm now going to do is I'm going to plot our ranges and our shear capacities. And that's going to be pretty simple. So X in inches and PV in kips. That's going to be pretty easy to do. All you have to do is literally all you have to do is type your ranges and your capacities as follows. It's pretty simple. So from 0 to 52. So just so you're aware, I'm getting these values from right here, from this table. So 0 to 52, 52 to 84, etc. So 0 to 52, 52 to 84, 84 to 124, 124 to 144. So if you notice, it looks like I doubled up on some values, and that's right. I meant to. Okay. So this first one is 86.72. So you can see I got that right there at the right end of this table. And just repeat that. So 86.72. Now, obviously, I'm typing these values out in Excel. You could obviously set this up to compute these values and whatnot. I'm just doing this to demonstrate. Oh. So the second one was 57.02. Repeat. This next one, 51.05. Repeat. 51.05. Repeat. Last one, oh, sorry. Last one, 27.32. 27.32. And then what you can do is you can go to this chart, go to design up top, hit select data, then add a series. Add all these X values, and all these Y values. Hit OK. And you can see getting the same plot. So if you're curious how that plot was generated in Excel, there you go. It's pretty simple. But really the main thing to point out is the behavior. See, that red dashed line represents the capacity. It represents how strong the beam is. And that red dashed line is always above the shear diagram. Um, it's always above that solid blue curve. Remember, the solid blue curve represents the forces that we're applying to the beam. The red dashed line is how much the beam can hold up. So for this particular example, this design is good because the beam is always strong enough to support these loads. It also makes a really important point about stirrups. For instance, if I just designed for what was going on at the support and used S equals 4 inches everywhere, well, at the support it would be fine, but here in the main body of the beam, I'd be wasting steel. So it makes sense out in the main body of the beam, and, towards the center of the beam where the shears are really low. Well, it makes sense to take your stirrup spacing and drop it. So hopefully this example sort of illuminated some of the math and the computations behind how you analyze for shear. In all honesty, structural engineers really don't analyze for shear very often. Usually all they're concerned about is design for shear. But I think this is really important because it gives you an understanding as to what it is you're doing and what the overall goal is. The goal is to produce a design where your resistances are always greater than your loads, and here you can kind of see it. What we're going to do in the next example when you all come back on Wednesday is we're going to learn and do some examples trying to determine for a given beam, how do you space stirrups to generate or to meet a given load demand. And we'll do that for a couple of different scenarios. We'll do that for scenarios where I'm going to skip ahead in the slides a little bit. We're going to do that in a couple of scenarios. So we're going to do it in one scenario where we have a uniformly distributed load, and then we're going to do it in a scenario where you have point loads. And the actual design process, the process is going to be the same, but because of the analysis, our resulting designs are going to have some significant differences. And I think the only way to do that is to actually just go through and grunt it out. But we'll have to spend some time looking at how do you design, how do you develop that design process, and that'll be in store for next time. So that's all I have in this video. I know we went a couple minutes over, but hopefully that cleared this up. So till next time, we'll see you all next Wednesday.